In this set of notes, we're going to continue looking at simple linear regression. And we're going to start out by talking about the variance of the estimators. So the greater the variability of the random error of epsilon, which is measured by its variance sigma squared. And remember, this comes from the fact that we're making that assumption that epsilon is normally distributed 0 sigma squared. So by this definition, that's why sigma squared is its variance. The greater will be the errors in the estimation of the model parameters beta naught and beta 1, and in the error of prediction when y hat is used to predict y for some value of x. So in other words, all this is saying is if we think of the errors as being how much we deviate away from our line, what this is saying is the greater the variability in those errors. In other words, if you think about how far spread apart we are away from the line, then of course we're going to have greater error in the estimation of not only our parameters, but any predictions we make using those lines. So consequently, we'll see that sigma square appears in all of the formulas for confidence intervals and hypothesis test. Because if you remember again from your intro stat course, one of the things that we have to account for whenever we estimate parameters is the variability of the statistic. And so this is directly relating back to that idea. So in most practical situations, sigma squared is unknown. It is a parameter. We know most parameters are unknown. So we're going to use the data to estimate its value. And the best estimate of sigma squared is s squared. You've seen this before. We generally know that whatever parameter we're interested in, the best estimate we have is that value calculated from the sample data. And s squared in this case is obtained by dividing the sums of squares of the residuals by the number of degrees of freedom associated with that quantity. And so here we use 2 degrees of freedom to estimate the y-intercept and slope of the model, leaving n-1 degrees of freedom for the error in the variance estimation. And so here we have our formulas that we're going to use, and again we're going to calculate these by hand here. That's just so you can see how this is done, but a majority of the time you're going to get these values from software. And so there's a warning here: make sure to carry at least 6 significant figures for each of these quantities to avoid substantial errors in the calculation of SSE. You'll see when I calculate these, I'm actually only going to use 4 decimal places. Again, this is just for illustration. In practice, I would never calculate these values by hand. I'm always going to use software. Alright, so we're going to continue our example that we had from the previous note set. And this example reads: a sociologist assigned to a correctional institution was interested in studying the relationship between intelligence and delinquency. A delinquency index ranging from 0 to 50 was formulated to account for both the severity and frequency of crimes committed, while intelligence was measured by IQ. The following table displays the delinquency index for a sample of 18 convicted minors. And so this is actually an abbreviated version of the table we had in the previous note set. So you'll notice I truncated it here in the middle. We have those same totals, the means, and then from the previous note set I pulled these values over. So we're going to calculate s squared and s for the delinquency index and IQ example. So to do this, we're still going to be working with some sums of squares. So these are going to be very similar to the calculations that we did when we got the estimates for the slope and the intercept. So notice we're going to start out with the sum squared y. So we're going to start by just plugging in these values. The first value here, the sum of the yi squared, we can pull that value from right here. Minus n is our sample size, and there were 18 sample points. And then y bar squared. And this value is equal to the following. And again, I'm only taking these to 4 decimal places because this is just for an illustration. If you were going to do this by hand, you would want to take at least 6. But again, rarely would you ever calculate these by hand. Majority of the time you're going to use software. Now we can find the SSE. So again, we have our formula here. So we start out with the value that we just found. We have our estimate of the slope from the previous note set. And we also found the sum squared xy in the previous note set as well. So our sum squared error in this case, 949.5549. And we can use this information to find s squared. So s squared is going to be equal to the sum squared error divided by the degrees of freedom. And then taking the square root gives us s. So next we're going to talk about how we can use these values to help us learn about our simple linear regression model and the fit of that model. So s squared is also known as the mean squared error, and s is referred to the root MSE. So we're going to start out by locating these values on the R and the Sas output. So this is the same output that we saw in the previous note set. In this note set, I have them at the very end of the notes. They're on page 7 and 8. So let's go to those pages and see if we can find the same values that we just found. And so before we do that, notice that s squared was equal to 59.3472. And so s squared is the same thing as the MSE. And then s was equal to 7.7037, and it is the root MSE. All right, so we'll go down to page 7. And we're going to start out with the R output. Notice here, down at the bottom, R has the residual standard error. This is actually the same thing as the root MSE. Now the default summary in R of our fit of our model does not give the MSE, but there are other ways to get that. And so when we work in the lab, I'll show you some of that additional R code that can give you that information. Next on page 8, we have the Sas output. Now the Sas output is actually going to give us both the root MSE and the MSE. So the root MSE is located right here, and then the MSE is located right here. So we get both of those pieces of information in the Sas output. Okay, going back up. Now, as always, anytime that we calculate a value, we always want to talk about what is the interpretation of that value. Why is it important? What is it telling us about our model? And so here, if we look at the interpretation of S, what it does is it gives us the estimated standard deviation of our errors. And we expect approximately 95% of the observed Y values to lie within 2 standard deviations of the respective least squared predictions Y bar. And again, this is coming from the empirical rule, and it has to do with that normality assumption. So the interpretation of S is as follows. So here we expect 95% of all of the delinquency index will be within 15.41 points of the predicted delinquency index using Y hat. So if you'll remember, we had this picture in the previous note set where we had our line, and this wasn't the line for this particular example, and it looked like as we went across different values of X, we had these normal distributions that went through the line. This isn't a great picture, but this is what this idea is getting at. What it's saying is that we could pick any X value, and where that X value meets our regression line, that is going to be our Y hat. And since we're assuming normality of the errors, what we're saying is within 2 standard deviations above or below where we are on the predicted line, that's where we anticipate all of our actual values to fall. The next quantity we're going to talk about is the coefficient of variation. So the coefficient of variation is the ratio of the estimated standard deviation to the sample means of the dependent variable y bar measured as a percentage. This measure is used to determine when that standard deviation is too large for the least squares prediction equation to yield useful predicted y values. So in other words, even if we get our predicted line, if it ends up the standard deviation is really large, in other words, where we actually expect our values to fall, are very far away from that predicted line, then that predicted line isn't going to be very useful. And so the CV, it gives us a way to measure that. And as a rule of thumb, we typically want regression analysis where that CV is 10% or smaller. And so we can calculate that coefficient of variation, this should say for the DI and IQ example. So here we have that would be equal to 100. S was equal to 7.7037, and then y bar from the previous page was 26.5778, and that is equal to 28.99%. Notice this is greater than 10%, so this model may not be useful. And again, it's because we just have too much variability. And what you're going to see as we move throughout the course, there isn't just one way to evaluate a model. There's really multiple ways to evaluate a model. When we need to take a holistic approach when determining whether or not our model is a good fit and whether or not it is useful. No model is going to be perfect, and it may be on some metrics the model looks really good, on some metrics it doesn't, and a lot of times it's just finding the best model given the data and the tools that you have available. And so in terms of the interpretation here, what we're saying is that the standard deviation of unaccounted error is approximately 29% of the delinquency index. Now R in its standard output does not automatically give us CV, but the Sas output does. So let's go down to page 8 and see where that's located in the Sas output. So looking here at the Sas output, notice right here we do have that coefficient of variation. And we could easily get that from R as well, it's just not included in the standard output. Alright, next we're going to talk about hypothesis testing for the slope. We're often interested in the expected change in the dependent variable y that is associated with a 1 unit increase in the independent variable. The change is given by the slope, because notice that's definition of slope, in the simple linear regression model. Almost always the parameter beta 1 is unknown, so it has to be estimated based off of that sample information. And so notice before we calculated the statistic beta hat 1. So now we're going to use that statistic to see if we can say something about the parameter and whether or not it's non-zero. So we always want to ask ourselves, is that x that we have, is it useful in predicting y? And so recall that the population regression equation is, or remember this is our model, if our slope were to become equal to 0, then we would just have y is equal to the intercept plus epsilon. So in this case, x wouldn't be providing any information about y, because if we think about what this model would look like on our plot, it would just mean that we have a straight line model. In other words, this mean or this line of averages would have the exact same y value for all of the different values of x. So if the slope were to be equal to 0, what that tells us is that x is not a useful predictor for y. And so we typically set up our hypothesis this way. Under the null, we're going to assume that the slope is 0, and we're going to look for evidence that the slope is non-zero. Now, in order to do this, you learned in the past, whenever working with statistics to perform a hypothesis test, we need to consider the variability of that statistic and the distribution that it follows. In other words, we're concerned with the sampling distribution. And so it ends up, if we make those assumptions about epsilon that we saw previously, then the sampling distribution of beta hat 1, that least squares estimate of the slope, will be normal distribution with mean beta 1 and have the following standard deviation. So in summary, if those 4 assumptions about epsilon are true, we get the following distribution for beta 1. And what this tells us is that the statistic beta hat 1 follows a normal distribution with mean beta 1 and standard deviation equal to sigma divided by the square root of the sum squared xx. And so kind of in a picture, here's what this would look like. And notice this picture is actually referring back to what we saw earlier if we're looking within 2 standard deviations. That again is referring back to that empirical rule. And we know that 95% of the distribution falls between those 2 points. Now, sigma is usually going to be unknown, so we replace it with s, and when we do that, we no longer get to work with the normal sampling distribution, we actually work with a t. And you saw this in your intro stat class when you looked at inference involving a mean. So usually when we look at confidence intervals or hypothesis tests for a mean, we work with a t distribution, and the reason for that is because we don't know the population standard deviation. So here we are going to be working with a t distribution. Remember that t distributions are defined by their degrees of freedom. So the degrees of freedom on this t distribution is going to be equal to n minus 2. And so we have our formulas here for our test statistic. And we call this particular test, when we're testing to see whether or not the slope is equal to 0, we call this the test of model utility. And this table here summarizes that test. And we're going to perform this for our delinquency index and IQ example. Alright, so what you're going to see as I work through this problem is all of this is things that, as the statistician, I need to work through beforehand. Now later on in the course, we're going to talk about how to write a method section for a paper, and what you're going to find is the work that we do here isn't necessarily how we report these results in a method section. So there really are 2 different components here. There are what I need to do as the person analyzing the data, and then how I need to communicate that in a journal article or in a method section. So just kind of keep that in mind, that when we get to that part, how we write up those results is going to look different than how we write them up here. Now, again, with any type of inferential procedure that I do, I always have to make sure that my assumptions are met. In other words, is it valid for me to perform this inferential procedure? So for right now, what I'm going to do is I'm just going to list out what the assumptions are, because we haven't seen how to actually check the assumptions. And so we're making the assumptions about the distribution of our error term. We're assuming that it's IID normal, 0 sigma squared. And we saw that before. And here I is equal to 1 up to 18 because we had a sample of 18. And then I'm just going to make myself a little note here. We're going to check this later. And again, that's because we haven't seen how to actually check these assumptions, but we do want to make sure that we state them. I'm also going to write down some information just so I have it. I know that I'm going to perform this particular hypothesis test at the 5% significance level. Now, there is current debate in the scientific community about how we report p-values and their relationship to the significance level. So what I'm showing you here is the more traditional approach, where we have that alpha equals 0.05. We're going to see if our p-value is less than or greater to that. But again, once we get to that method section, we'll talk about how the reporting of this has changed some. We have our hypotheses. Now again, this is a model utility test, so under the null hypothesis, what we're going to do is we're going to assume that the slope and again that is the parameter, is equal to 0. And we're going to see if based off of our sample information we can show that that slope is non-zero. Now in order to do this we do need to account for the variability. So in order to account for that variability we're going to do our first calculation. So we need to find the S sub beta hat 1, and if we go back on the previous page and we look at our formulas, you will see this value. Now previously we have calculated both of these, so I'm just going to substitute these in. And again, I would, this is just for illustration. In practice, I'm always going to use software to find these. And then from here, now that I have that variability, I can calculate my test statistic. So my test statistic, again in this case, since I am having to estimate that standard deviation, it is going to be a t-test statistic. T-test statistics need a degrees of freedom. So in this case it's going to be n, which is 18 minus 2, which is equal to 16. And then the formula for my test statistic is as follows. These are values that we've already calculated or found previously. And now that we have that test statistic, the next thing we need to do is we need to find our p-value. Now in lab this week, you saw how to find area under different curves as well as endpoints. This comes in handy when we need to find p-values or later on when we need to find critical values. So talking through this test statistic does come from a t-distribution with 16 degrees of freedom. So if I were to draw a t-distribution, so this is a t with 16 degrees of freedom, what I'm saying when I'm looking for the p-value, since this is a two-tailed test, I want to mark negative 2.1570 here and the positive value here. Now the t-distribution is symmetric, and so the p-value is equal to the area in both of these tails added together. And as you saw in lab, we can use R to help us find that. The R code is going to give us the area to the left of a particular point. So if I wanted to find the area to the left of negative 2.1570, in R I could do the following. I could use the pt function, negative 2.1570, comma, give it the degrees of freedom. And remember, since this area is the same in each of the tails, I could then multiply this value by 2, and that would give me the p-value. And if you put that in R, you would find the following. So notice here that since 0.0466 is less than that 0.05, we are going to reject the null, and our results are significant. So to write a formal conclusion in words for this problem, we would say the following. At the 5% significance level, we conclude that IQ contributes information for the prediction of delinquency index using a linear model. And I'm running out of space here, so I'm just going to move down to the next page. And we can say further, the linear relation, or pardon me, further, the data suggest that the linear relationship is negative. And this comes from the fact that the slope was negative. And we can find all of these values using both R and Sas. So let's find those. So notice our test statistic here was negative 2.1570, and our p-value was 0.0466. So looking at our R output, if we look right here, you will find that test statistic and that same p-value are very close up to rounding differences. And then looking at the Sas output, we can find that information right here. And again, this is the same up to rounding difference.